Okay, so I think we can go ahead and get started here. Again, you can feel free to add some feedback if you'd like while we're getting rolling. But yeah, welcome to week number 6. We have basically this week and one more week left in the course, so time goes quite quickly. And we have a couple important topics still yet to cover, and we'll get into a little bit more stuff with pandas today. And then our last week we'll be looking at data visualization. But yeah, having a look here at the feedback first, what you can see here is, well, at least one person that was of the opinion that week 5's tasks were nice and somewhat simpler than the previous week. I'm actually a little bit surprised to see that because normally the feedback is more the opposite, that week number 5 is harder than the week before. But, you know, of course, this varies from person to person. And, you know, for some people, I think the concept of a function is a little bit of an abstract thing, and maybe the exercise, you know, doing the basics with pandas makes a little bit more sense. And, yeah, I mean, I think this is good to see overall that people are feeling that the week went fairly well and that they're understanding things a bit better. That's good because we're going to build on that in this week's lesson. So we take what we learned last week in pandas with our basics, and now we add a few additional new skills that you'll learn to be able to do some data analysis type operations. And this is kind of a natural thing to do with pandas because pandas is, after all, a library that is used for data analysis and data science. And also happy to hear that for those who decided to continue working in pairs, at least some seeing that the working in the pairs was helpful for this week's exercise. This is basically the idea behind having you work in pairs, is that you've got another person you can talk to and you can discuss things, and hopefully between the two of you find solutions to any of the problems or issues that come up during the exercise or when looking over the material from the previous week's lesson. Is there any other feedback, maybe from anybody who wants to say anything about week 5 before we continue on to today's lesson? Okay, yeah, well, if that's the case, then I think what we can do is have a look at the course webpage, make this a little bit bigger so we can see it. And again, we are in now to week number 6, lesson 6 on the course. And as mentioned, we're going to continue working with pandas in this week's lesson. In fact, I think this is one of the more fun lessons in a sense, because you really get an idea of why learning Python for doing things like data analysis is a worthwhile task. And I hope that you'll find this to be interesting. When we get into the lesson, I'll tell you that it's not quite the lesson I was hoping to have for this year, but you'll see that nonetheless it's an interesting opportunity to do some data analysis. In addition to what we'll talk about with pandas this week, we're also going to talk a little bit about dealing with different error messages that you might encounter in Python, so kind of how to interpret the error messages that come up when different types of errors arise. We've already seen some of these kind of common name errors and index errors, things like this that are indicating a problem with the code that you might have in one of your cells in the notebook. But we'll investigate those a little bit more closely and also talk a little bit about debugging your code and ways that you can try to be more efficient in finding problems with your code. And this might be something that's kind of useful for the final exercise in the course, for example, because there you'll have a little bit more freedom and you may make some mistakes you don't normally make in the exercise as a result. So anyway, yeah, basically we're going to learn to do some data analysis with pandas, kind of building, like I said, on last week's skills. We'll learn how to repeat a workflow for multiple data files. That's something we'll do at the end of the lesson. And then also do this stuff about errors and debugging. So yeah, you'll find the lesson materials on the course webpage, but of course, As usual, we'll be working here in Jupyter Lab, so I'm in the CSC Notebooks platform now, and what I'm going to do to get started is just go into my work folder, to the notebooks, and then I'm going to pull the changes by going to the Git plugin, and then it should show that there are things to pull down from the remote. So I can see the little orange circle. It indicates there's changes in GitHub, and so I'm just going to click this and pull down the latest changes to my local copy here on the CSC notebooks. If anybody has trouble with this, just let Kamyar know, and he will try to assist. Most often the case is that if you've committed changes in your local copy on the CSC notebooks and you go to pull things, you might get an error message saying it's unable to pull because it can't resolve the differences between what you've modified locally in the CSC notebooks and what's on the GitHub. And usually what I've been telling people to do is basically just make a new copy of the notebooks repository. So you can just go and rename, for instance, here you could rename the notebooks folder, and then you can follow the instructions from the first week of the course on how to pull down the changes. So if you're wondering, if you're having problems that you can't pull your changes, you can rename your notebooks folder to something like notebooks old. And if you go back to the course page in the course environment, and I think it's in this cloud computing environment section from the first week, somewhere down in here, you'll see this information about, after launching the Geo-Python workspace the first time, how to clone the notebooks repository. That's usually the fastest solution, because resolving merge conflicts is not something we go into, but it can be a bit of a hassle, and it's worthwhile to learn at some point, but it's in the interest of time usually faster to follow the instructions on the course page for pulling down the notebooks repository again if you're having problems. But for those who were able to pull things down, you should see now there's the L6 folder in the notebooks, and we're going to go to this advanced, I think it's advanced data processing with pandas or something like that is the name of the notebook, but you can just double click on the one that starts with advanced. And then I'm just going to hide my file browser. I think there was maybe one other person coming on the left side. Okay, so let's talk a little bit about what we're up to in today's lesson. We'll start with our motivation, which is here. I'm going to maybe make this a little bit smaller so we can see the whole image. But of course, it's not really totally shocking news that we've been having these anomalously warm temperatures every once in a while. In fact, if you look at the warmest years on record, many of them occur within the last decade. And of course, there are warm months within those years as well. And for instance, April of 2019 was a notably warm month in many countries in Europe and in many parts of Finland. This was one of the warmest Aprils on record. So you can see, for instance, here, the amount of the kind of deep red color indicating the departure from normal, and in this case, temperatures that were on average 4 to up to 8 degrees higher than the average April when you compare to what April's normal temperatures were in a reference time period from 1951 to 1980. So it was warm. I don't remember off the top of my head particularly notable things about that April, but you might have recognized that this past September was also exceptionally warm. I was hoping to give us the opportunity to explore the climate data and do our same exercise by looking to see how warm this September is compared to previous years. But there were some issues with the data server where the climate data was hosted, and unfortunately, I wasn't able to pull down new climate data in time to update today's lesson. But the point, regardless, is that we would more or less go through the same set of operations, just picking a different month to explore. And perhaps this is something that we'll be able to do next year in the course, because this year's September was quite significantly warmer than normal. It was more than a degree hotter than the past several Septembers, which of course have been following a warming trend as well. So yeah, it will perhaps jump out even more than our April 2019 exercise. But anyway, that's the point for what we're going to explore in today's exercise. So this is just an example of a news article from weather.com indicating that 13 locations in Finland had their record warmest April in April of 2019. I don't think that's been beat yet, but the data set we're dealing with only goes up to maybe 2020, so we won't be able to look at the most recent Aprils. But I still think this holds as the warmest Aprils in recent history. Now I'm going to make this a little bit bigger so we can see. So in order to do what we want to do today, we have to go through a few different steps in our data analysis, doing things we didn't do last week. So notably, we're going to do, first off, some renaming of columns. This is basically just to make our data easier to work with, to give our columns in our data frame names that are perhaps more clear to us as users. Then we'll talk about how to iterate over data frame rows and to use functions to do calculations on rows of data frames, and also how to do that in a sort of more efficient way by applying the functions. Then we're going to do some data aggregation, because the data that we're dealing with are not monthly temperature values, but they're much more high resolution than that in terms of time. I think there might be multiple observations per hour. So we want to basically introduce how to take things like hourly or multiple temperatures per hour and calculate average for instance, for each month from that data set. And then we'll talk at the end about how to repeat this over many different data files and show an example of that. And the data that we're working with is also, it's been downloaded from the U.S. National Oceanographic and Atmospheric Administration website, which I believe, at least as of 7 o'clock this morning, is not up. So this is the reason why we don't have updated climate data. It was up earlier last week, and then it went down, and it doesn't seem to tell why. So anyway, it's not working, but in principle, you could go and download the data yourself. And we can skip over this section about downloading the data for those of you who are on the CSC notebooks, which I think for today I would say, please, everybody should be working in the CSC notebooks platform, because this is not a good exercise to do with Binder. But yeah, we can just skip over this downloading the data section, and I'll show you why in just a moment. So I'm going to skip ahead here to the description of the data, and then I'll show you why we don't need to download it. So you'll see that with our data that we're working with for today, there's a few different metadata files. So these are things that are describing the data that we're working with. So one of them is this list of stations. So if you click on that, if you're interested, I think it can somehow change the view so it doesn't wrap the lines. You'll see that we have, in this case, data from, I think there's 15 different stations here in Finland. So a bit more in terms of the number of stations that we're working with compared to years past, previous lessons rather. So you can see these are all the different stations that we'll be working with. That's listed in this one metadata file. Then there's also information about what data is available at each station. So you'll see for each one the year, and then how many observations are available per month for each year. So you'll see, for instance, in Sodankylä that there were 93 observations in January of 1917, then 84, 93, etc. This is something like maybe 3 times a day that these temperatures are recorded at the beginning. But you'll notice that the number goes up with time. So the frequency of the observations is changing through time, such that by 2019 we have 744 observations per day for the temperatures at, observations per month for the temperatures at Sodankylä. And you can see the same thing for others. You can also notice that there are certain times when there are no observations. Like in 1957 in Kuusamo, there's basically the first 9 months of the year where there's no temperature observations whatsoever. And finally, then there's a data description, and this is essentially just telling you what the different columns in the data file mean. So if you're curious to look through that, you can have a look there. It's very useful in many ways when you download these kind of data sets to take not only the data, but also these metadata files so that you understand what you're working with. But if you look at one of the data files that we have here, what you'll see is a bunch of column headings that look like this. And some of them make sense, some of them don't, but we'll load the data in and take a look at things in more detail in just a moment. But obviously you can see there's quite a variety of different things here, and you'll also notice that these column widths, I don't think there's an easy way for me to make this not wrap the lines in the view we have here in JupyterLab. I'm pretty sure that won't let me do anything, but maybe we can take a look at the data file in just a second, and you can see a version without the lines wrapped that makes it a bit easier to see. These columns are all fixed width, so they're not comma separated in this data file. This data file is more or less in the format that it was pulled down from the server. And so the column width is fixed, and you'll also notice here these asterisks, and what they indicate are places where you're missing data. So with a comma separated value file, you just have the comma, and if there's nothing between two sets of commas, it indicates that there's missing data. But when you have a constant width of the column, you have to fill in something there to indicate whether there is or isn't data recorded. And in this case, the symbol that's used is an asterisk or a little star. And what makes this a bit tricky is that depending on the width of the column, you have different numbers of stars to indicate missing data. So this is a bit nasty to deal with this data file, and we're going to have to use a couple new skills to be able to do that. So yeah, I mentioned that we don't need to download the data. Let me show you why. If you're working in the CSC Notebooks platform, you should see, if you go to this folder that's the kind of home directory in the file browser, there's a shared folder that we haven't used before. And if you go into the shared folder, you'll see there's a directory in here called data, and the directory in there called L6. This is where all the data files for today's exercise live, and what's nice is that with the CSC Notebooks system, we're able basically to have one folder where you can all see the data files without having to download them individually. That's quite handy. The one that we're dealing with is this 029440.txt, so we should be able to find that in here. There it is. And if we double click on that data file and we wait a moment, it should pull up here in the text editor in JupyterLab, and we can then see what the file looks like. I think it's a decently big file, so it might take a moment here to render in JupyterLab. If I'm not mistaken, there's something like 750,000 temperature measurements that are in this data file, so it's a bit bigger than some of the files we've dealt with in the past. Okay, I thought this would open a little bit faster. There it goes. So now I'll just, again, put the view so that the wrapping of the lines isn't there, and perhaps you can see more easily now that these columns are indeed fixed width. And there are some things that maybe make sense here, like this is something related to the date. So there's year, mode, hermun is year, month, day, hour, and minute. And so you can see, for instance, here, our data set starting in 1906 on the 1st of January at 6 o'clock in the morning. And if you scroll over to the side, there's other columns you can see as well that might be useful, like temp. So that's going to be the temperature that was recorded at that time. And we'll be working with our data file that looks like this for the rest of the exercise. Now, if I jump back to the notebook, and I'll just hide the file browser again, our starting step is we need to import pandas. So we'll just import pandas as PD, normal, standard operating procedure for working with pandas. And we just took a quick look at the data file, and this data file, I guess, is for the Tampere Pirkkala station, and we saw how it was structured, and I've already noted these things about the delimiter. In this case is spaces. So as you can see between the columns, there's a space or multiple spaces. Again, that makes it a little bit tricky because it's not consistent. And the no data values are indicated with these asterisks. So we can just run a couple of the cells here. The first one's going to set the file path to our data file. As noted, it's in this shared directory and in a folder called data and then L6, and then there's the file name. So we're just defining this variable fp that will tell us where the data file is located. Just going to run that cell. And then you can see here that I've also already included the format for the read CSV function. We don't need to type this in because you guys have already read in the data files before, but I'll note a couple things rather. One is that we're going to use this parameter called delim whitespace equals true. So the note up here about the varying number of spaces between the columns. When reading a CSV file, there is this option to use this parameter. It basically says that you should treat the spaces between columns as the delimiter. So rather than like a comma that we saw last week, delim whitespace equals true will essentially say that, okay, whenever you encounter blank spaces between values, that's a separation of the columns that will be read into the data frame. And if there are more than one space or a single space, it's treated basically equally as a separating character. The other thing that's different from last week is now we're using the NA values and then giving a list of different things to see as NA values. So whenever it sees a star, 2 stars, 3 stars, 4 stars, etc., it will treat those values as missing data and convert them to no data when reading in the data file. So just run this one as well to read in our data file for today, and you can ignore the warning message that pops up here. That's nothing to worry about. Okay, so now we've read in our data to this variable called data. We could do data.head, for example, to take a look at what we just read in. And this is good place to start. You can see that it looks like we have our different columns like we saw in the data file. The headings here seem to be making some sense, and then the values underneath there are being converted properly to missing data, or NaN, not a number, where they are in fact missing. So this looks good overall, but there's a lot of columns in here that we don't need. And I think in all it says 33 columns here. And, well, we don't need all those, but if we take a look at all the different columns that we have, we can just type in data.columns and run this. And you can see the names of all the different columns that are here. We're basically looking for temperature anomalies, so we can rule out working with a lot of the things here and just focus on those columns that are perhaps of most interest to us. So let's read the data file in again, kind of like we did last week in the lesson. This time we'll read it in with the same file path, the same delim whitespace, the same NA values, but we're going to list here use calls and then a Python list with the different column names we actually want to use. So USAF is that's the station identification column. This is our date. Then we have the wind direction, wind speed, and the gust of wind. We don't, strictly speaking, need those, but we can read them in all the same. Then we have a temp column, and then max and min, that would be the maximum and minimum temperature that's recorded on that day. So again, we can just run this to read our data in once again, and then it will do a data.head at the end of the cell. And now we've got a little bit more manageable data set to work with in the sense that we don't have so many wasted columns. Again, we're going to mostly be focusing on the temp column and perhaps the max and min, but you can see our station identification character code or number, and then our date, wind direction, wind speed, gust, and temperature, and then the max and min. So this looks good. I think we're okay to proceed at this point. But what we can do here now is take some of these column headings we have and perhaps convert them to things that make a little bit more sense to us as users of the program that we're working with. And so what that means is we're going to do some renaming of our columns, and we're going to start by learning a little bit about how to do that. Okay, let's just check first by typing data.columns what the names are that we have, and you can see we have this same list that we saw in the heading when we did data.head above. The way in which we're going to do the column renaming is going to involve learning about a new data type or new kind of structure we haven't used yet in Python called a dictionary. And dictionaries are kind of neat. They basically allow you to link one value to another. So you have a key, and you can link that to a value, and we'll see how to do that in just a moment. But the idea to start would be that we could take this clumsy way of referring to the date and time and just rename that as time. And we could take SPD and rename that to speed, and GUS and rename that to gust, so that we can see these different things more easily within our data frame. In order to do that, we need to first connect these original column names to the name that we want to use, and we'll do that using a dictionary here that we can call new_names. When making a dictionary, we've seen with Python lists that we use the square brackets. We haven't used tuples, but they use parentheses. But with dictionaries, we're going to use these curly braces. And then what we do is we put in one of our old column names, like year, mo, da, her, moon. So year, month, day, hour, minute. Put that in quotation marks because that's a character string. And then the expectation is that you have a colon character, and then the new name that you want to have for that column. In this case, we want to call it time. With our dictionary, we can do multiple of these renamings at the same time. So we can also then take SPD and convert that to speed. And I guess I can put a space in here just to make this more readable. And finally, then we can take Gus and rename that to gust. So in this case, each one of these things that's listed first would be the key, and then the value that we're going to link to that is time. The way that the dictionary would normally work in Python is that when you use the dictionary and you put in the key, you should get the value that comes back. So like if we typed in new names and then put in your, mo, da, her, mun, we would get time back, and pandas is basically going to use that same kind of approach to do the renaming of the values. In fact, just to demonstrate, why don't we just copy this and make another cell? If we take our new names dictionary and put it down here, and then we type in new_names, and then let's put in SPD. What we should see is when we run this is that we get back speed. So this original thing is being used as our key, and it's finding that it's linked to this value here called speed, and that's what gets printed out to the screen. And if you typed in any of the other ones, I typed in SPD just because it was quick, but if we typed in your mo, da, her, min, of course we'd get time back from our dictionary. So again, it's linking a key to a value, and we're going to use this trick in pandas to allow us to rename the columns. So we've typed in our dictionary above, we run this, and we get back basically the same thing we typed in. It's a Python dictionary with our different columns in there. Now, let's rename them. How do we do that? Well, with pandas, it's relatively straightforward to do. Actually, before we do that, let's just check our type of our new names. Because we can use the type function, And if you run this with new names in here, you should see it comes back as dict, meaning it's a Python dictionary. So that looks good. And no surprises there. But let's take this and now rename our columns in our data frame. So we'll start with data equals, and then we're going to do data.rename. And then inside here, the parameter we'll pass is called columns. And we'll say columns equals new underscore names. So the rename function is basically going to look in our dictionary, and everywhere it finds one of these column headings like this, it's going to replace that old column heading with the new character string that we've listed in the dictionary. And if we run the cell like this, you'll see now that when we do data.columns, we get USAF. Okay, we still had that one before. But now we have time, dir, speed, gust, temp, max, and min. So it basically has worked properly in renaming the columns as expected. Now you can have an opportunity to test this out, practice. And what we're going to do in this case is rename 2 additional columns. So for one, we're going to be converting our temperatures eventually from Fahrenheit to Celsius. So let's just call the temp column temp F to avoid any confusion. We can also rename the USAF column to be called station number. And yeah, basically you can follow the same example we did above and see if you can rename the 2 columns as listed here, and we'll continue in a moment after you have done that. I think it is possible. The best way to figure this out would be, we can check the documentation. I've only ever used it for renaming columns, but it does say rename columns or index labels. So in principle, yes, if you had index labels, particularly if you were using something where like it was not just a 0, 1, 2, 3 type index or not a date, because renaming a date would be a bit weird. But I guess depending on what you were doing, you could potentially, like if you calculated from climate data like the temperature for the summer, you could rename the column to be called summer instead of like some weird mix of dates that might be there. So yeah, it does look like it's possible to do that. You can also, just to note, we did data equals data.rename, but you can also do the in-place, use the in-place parameter here to basically just replace the column names inside the data frame without having to say data equals. If you add the in-place equals true parameter, it will just update the data frame. But generally speaking, I don't like to do that personally. I prefer to kind of always make it clear when I'm updating something in the notebook. But yeah, was everyone more or less able to get this to work? Or anyone having trouble still? Okay. So yeah, let's first make our dictionary. We can just demonstrate this quickly. And one thing I want to note is that okay, there's nothing special about new names. We could call this dictionary also new columns or whatever you want. Hopefully something that makes a bit of sense. And so we had the task of converting USAF from that key to the value station number. And then we add a comma. And then our next key value pair is that we want temp to be renamed to be called temp underscore F, just to indicate that it's Fahrenheit temperatures. Then we said data equals data dot rename, and then columns equals, and in this case, I'm going to call it new underscore columns because that's the name of the dictionary that I've created. So when I run this one, hopefully you had similar results. You see now station number and temp F as the 2 columns that we have we've created, or renamed rather. All right, let's have a look at our data frame because we loaded this thing in. We saw that everything looked okay in terms of the columns we have, but let's take a look at some of the basic information we have about this data frame. So we can first do our data.shape, which will give us the number of rows and columns. So you can see, for instance, there are 757,983 rows and 8 columns. Well, you can count the columns pretty easily, but of course we don't want to count the rows. But it's a fairly decent sized data file. We've got 750,000 temperature observations. And we can do, for instance, data.head, as we've already done, to take a look at the top rows. So you can see a few things that are notable here, like our data set starts in 1906 on the 1st of January at 6 o'clock in the morning. And if we did data.tail to check out the last 5 rows of the data file, we can see our most recent observation in this case was from 2019 in the month of October on the 1st at, 10 minutes before midnight on that date. We can also do data.dtypes, to be able to see what kinds of data types we have for our different columns. So we can see, for instance, station number and time are integer values, whole numbers, whereas all the other columns are floating point values or decimal numbers. And okay, that makes sense. When we look at station number and time, they are indeed whole numbers, and all the other ones have decimal points or not a number if they're missing data. That's good. And we can also do, finally, our data.describe function, which will calculate the sort of descriptive statistics about the data set. The most notable of which, perhaps, is that if you look at the count column, that tells you how many values you have for each one of the columns. You'll see that there are 757,983 for the station number. Okay, that's good. That should be there every time. Same number, a little bit different format for the time. But if you look at some of the other columns like gust, you'll notice there's quite a few missing, only 19,000 or almost 20,000. Temperature F has a lot of the values there, but the max and min are missing many of the values for the data set. So data.describe can tell us something about the statistics and the values that are here, but it can also tell us very quickly how much data we're missing from different columns. So we can see we're missing a bit of data. Any questions about renaming columns or anything like that at this point? Okay, so now we know how to rename columns, and we can move on to our next step, which is to use functions in pandas to do some calculations from values in our data frames. And in this case, our natural choice is to use our favorite function to convert Fahrenheit temperatures to Celsius. We've already done this several times, so we don't need to type the function in. We can just run the cell to define it. But we're going to convert our temp F column values into a new temperature column called temp C. And here's the familiar function by now for converting Fahrenheit temperature to Celsius. We'll just run this to define the far to Celsius function and make that available for our use. And just to make sure everything is working properly, we can type in far to Celsius and pick a temperature that we know should convert nicely. So there's a few handy ones. So in case you're ever curious about converting temperatures between Fahrenheit and Celsius in your head, a fun one is that 82 degrees Fahrenheit is 28 degrees Celsius. So you just flip the numbers, or 28.7778. Okay, so effectively it's 28 degrees. If we pick a temperature like 32 degrees Fahrenheit, that's the temperature where water freezes, and of course we get back then 0 as the temperature Celsius. But yeah, you could also, for instance, take 68 degrees Fahrenheit, which is kind of room temperature, and that's 20 degrees Celsius. There's a few somewhat familiar values that we could use to test this, but the function's working properly as expected. And before we go any further, let's just do data.head one more time, just to remind us of what our data set looks like. Okay, So now we're going to learn how to be able to use functions like this to calculate values and convert, for instance, starting by iterating row by row, converting all the temperatures from a value in Fahrenheit to an equivalent value in degrees Celsius. And for this, we're going to use a method called iterrows. And iterrows will allow us to basically go through our data frame row by row and do something with each row. And what's unique about the function, in a sense, is it allows us to go row by row, but it also gives us the index value of each one of the rows as we're working our way through there, which can be helpful for instance, knowing where we're at with the processing of the data in the data file. So we have a cell here already filled in where you can see a for loop. So of course, when you iterate over things, it's very typical to use a for loop. So you can see here, though, that instead of a single variable, we have two variables separated by a comma. And that's because data iterrows will give us back the data for that row, but also the index for that row. So there's two things that come from that function, which is why we have two variables here instead of a single, more typical view of a for loop where there's only one variable there. And what we'll do in our test case here is we'll just print out what the index value is. We'll print out what the temp f value is for that row. So you can see here row and then temp f. And then we'll print a new line character just to give us a blank line after that. But then we have something new here, which is a break statement. So oftentimes when you're testing things with a for loop, it may or may not make sense to go through every one of these 757,000 lines of this code and run the whole thing, but maybe just go through one, and the break statement will then stop the for loop after that. So when we run this cell, we'll get one row of processing of our data file, and then the for loop will get broken out of, and it won't continue the for loop after that. So if we run it, what we see is index 0, temp f is 27, and then it stops because of the break statement. So quite handy when you want to do something like this test and see, did we use the data iterrows properly? And let's have a look here. If we scroll back up, here's index 0. The temperature for that observation time is 27 degrees Fahrenheit, so it looks like this is working properly. There's a little bit more description about breaking a loop on the course page that you can see, or you can see in the notebook here. But now we can take this basic idea of doing this for IDX, which is our index variable, and row, which is our row variable, in data iterrows, do some stuff with that. And as you saw last week, we can make a new column called temp C, for example, by just typing data and then in quotation marks temp underscore C equals 0. So we'll just fill the thing with zeros to begin. And then for IDX, comma, row in data.iterrows, this is basically the same thing we just typed in to go through row by row and do something. We're going to first calculate a value called Celsius, which is our function far to Celsius with the temperature in Fahrenheit from the current row. Then, after we've calculated what the temperature in Celsius is for that temperature in Fahrenheit, we're going to use the data.at locator to go to our index, which is going to be whatever row we are in our data frame, and the column name temp C, and fill in the temperature that we just calculated in Celsius. So as we go through row by row, we're going to first convert from Fahrenheit to Celsius, and then we're going to fill that into the place where it should be saved in our data frame in the temp C column. We could do this with the data.loc as well, but when you're referencing a single location in a data frame, data.at is faster. So data.loc is normally used to get a range of values from a data frame, not a single value. So that's the main difference. But if we run this, and if you've started running it already, you'll notice it doesn't run instantaneously. It takes maybe 20 seconds or something like that to do this, because it's going to go through each one of the rows and do this kind of operation where it converts the temperature and then stores it, converts and stores. And that's actually not a very fast thing and not a very efficient way to do things in dealing with larger data sets like this one. but it's the closest to what we've done so far. So before we see another way to approach this, we thought we would introduce this method first. So maybe my 20-second estimate was a bit of an underestimate of how long this takes. But you can see it's not particularly fast, and you'll note it's quite significantly improved when we do this with a different approach in just a moment. Okay, so there it goes. Now it's finished running, and yeah, we can then take a look at our data frame once again by typing data.head. We expect now to see a new column called temp.c that contains our converted temperatures from Fahrenheit to Celsius. As a reminder, 32 degrees Fahrenheit should be 0 Celsius, so a temperature of 27 degrees should be just below Celsius, and it looks like these temperatures are correct at first glance. So it looks like this worked properly to create our temp.c column and fill it in with our temperatures in Celsius based on those that were there in Fahrenheit before. Now I mentioned that there's a faster way to do this. So let's have a look at how to do this a little bit more efficiently in using what's called the apply method. So for this, we can now take our data from our whole column. So if we say data and then temp underscore F, this is all of our temperature Fahrenheit values. And if we type dot apply, and then the name of the function we want to use to analyze that data, in this case, far to Celsius, without the parentheses after it, you can run this, and you'll see how much faster it is to do this all at once for a whole column. I don't really want to go into the details of exactly how this works under the hood, but it's using a library called NumPy, and NumPy works with data that's in arrays, and this single column out of our data frame is essentially, it's very similar to a NumPy array, and NumPy is very efficient for doing things like this kind of calculation for a whole column of values. So when we ran this cell, I mean, it took less than half a second to calculate all the temperatures in Fahrenheit, and you end up with more or less the same result. Now this is just done the calculation and output it to the screen. If we wanted to store this in our data frame, then we would want to do something like data and then temp underscore C equals, and the same thing we typed above. You can just copy paste this if you want. Be a little bit faster that way. So this will just assign the values and overwrite what was in the temp underscore C column again, just like that. In fact, we can do this with multiple columns at the same time if we want to, because you remember that we have this max column and the min column that also contain temperature data. They're also in Fahrenheit, and we can just go ahead and convert those at the same time. If we wanted to, we could do data, and note here that we have to have 2 sets of the square brackets, and that's because we're going to put a Python list here of the columns we want to convert. So there's temp underscore F, there's max, and there's min. So because this is a Python list, and there's only one value that's expected to be here, it's 2 sets of the square brackets, and then dot apply, and then the far to Celsius. We're not going to store the output of this into our data frame. We're just going to run it just to show you can do this to multiple columns at the same time, and it's still pretty fast. So in this case, it's perhaps not a huge surprise if you remember that max and min were mostly missing data. I think there was maybe 30,000 values there total, but when you convert all 3 columns at the same time, it's pretty efficient and pretty fast. So this is perhaps the preferred way to do this kind of use of functions when you're working with larger data sets. So now we have another opportunity for you to test things out. So just like we showed for converting multiple columns at the same time, you can now try and do the same thing to convert tempf, min, and max all at the same time and store them into our data frame as new columns called tempc, minc, and maxc. So, I mean, in effect, you're going to overwrite what is there in the tempc column to begin with, and you can enter your solution into the cell below here, and we'll continue in a moment after you've had a chance to do that. Okay, if you're still working, that's fine, but for those who are finished, I'll just go over the solution here, and if you don't want to know it yet, then just don't look at the screen. But what we're going to do here is we want to fill in 3 new column values at the same time, and just like when we want to reference those multiple columns at the same time, we have to use a Python list, and so that's why we have inside here the double brackets. And then our columns we want to create were called tempc, max or minc, and maxc. And those are going to be column values that we fill in by doing data, and then we give again, oops, wrong cell, the list of columns we want to convert from. So we had tempf, min, and max. So these are columns in the data frame that already exist, and we want to convert them by applying our function. So we then do .apply and then the name of the function. So like this, we'll take our 3 columns out of the data frame and apply this function to convert them, and then store those values into our data frame as the 3 new columns, tempc, minc, and maxc. Okay, tempc already exists, we'll just overwrite that, but otherwise we have 2 new columns. You run this, again, it's quite fast, and if we look at the data frame contents by doing, for instance, data.head now, you should see when you run that we have tempc, minc, and maxc here. So our new columns have been created as expected. And note that in doing this, we actually reordered them so that we have temp, min, and max rather than temp, max, and min, but it doesn't make much difference. I've already talked about the importance or the sort of benefits of using apply over iter rows, but you can read that on the course page if you'd like. And I think why don't we go into this parsing dates a little bit? We're going to take a break in the middle of this lesson, I think, or toward the end of this lesson, because there's a bit too much to kind of fit in before the break without making you guys completely miserable. So we'll talk a little bit about parsing dates. I don't know if we'll get through this before we take a break, but we'll take a break here shortly. So just so you know, it's coming. Okay, so what we want to do now in parsing our dates is to take the steps we need to be able to go from observations that are maybe multiple temperatures per day, multiple temperatures per hour even, and get them to the point that we have them as like a single temperature for the month of April of some year. So if we take our data and we look at what's in the time column right now, we could do data.time and then head, and let's just like make this head 10 so we can see the first 10 rows. And what you can see is that we have these pretty regularly formatted dates: 1906, 0101 at 6 in the morning, 1906, 0101 at 1 o'clock in the afternoon, and then 1906, 0101 at 8 p.m. or 8 o'clock in the evening. And this pattern sort of repeats. So we have the year, the month, the day, what hour it is, and then what the minutes are of that hour. We can take advantage of this. Well, I guess we could also maybe, let's do data.tail. And again, we can look at the last 10 values. Sorry, this should be data let's just get the time column so we don't have to see all this other stuff. But you can see the same format works later on in the data file as well. So our first observations from the 1st of January 1906, and the last is from the 1st of October 2019, 10 minutes before midnight. And we know that our type of our data, if we looked at data.dtypes, and we look just in our time column, we have that it's an integer value. We saw that before, no surprises there. In order to go from working with this data that's of higher sort of time resolution to something that's more like monthly values, we're going to first need to convert our time from being an integer to being a character string. And I'll show you why that is in just a moment. But we have to convert to a character string. So we can make a new column here called data, and let's call it maybe something like time_str. And what we can do in our time_str column is take our data time column and use the asType function. So this will allow us to convert from one data type to another. And we'll do asType str. So we'll take the values that are in our time column right now as integer values and convert them to strings and then store them in the new column called time_str. Same number, but now it'll just be wrapped in quotation marks. The benefit for that is that when you have a character string, you can do what's called string slicing. It's kind of like index slicing that we saw last week when we wanted to pull out certain range of rows and things like that from a data frame. We can do the same approach to pull out a certain number of characters from one of our strings. And it looks very similar. So for instance, if we had a date, so if we said our date is equal to, and let's put this in quotation marks, let's take the last day of our data set. So 2019, 10:01, and then it was 23:50 was the time. You can put in some other number if you type this in wrong, it doesn't make a huge difference. But if we then define that date, and then we take our date and say, let's do a slice of our date, starting at the character in position 0 and going up to, but not including, the character in position 6. You can kind of think of each one of these positions like an index value in a Python list. So the character at position 0 is 2, then at position 1 is 0, and so on. Such that when we run this, what we do is we get out of here the range from basically the first 6 characters, so 2019, and then 10. What's nice about this is now, from this date, we have only the year and the month. And we can take advantage of this because if we do this for all of the dates that we have in our data frame, for example, we can make it so that we see only the year and the month of the time that's recorded with that given observation. And then we can start doing what's called grouping, where we take all the values that have the same year and month and do something with them. And I'll show you what that something is in just a moment. But let's first take this idea and apply it to our to the dates that we have here. So we have our time_str column that contains our character converted values of the date and time. And we could take our data frame and make a new column in there called year_month. And we can take our data time_str and we'll use this method in pandas called str.slice. It's very much the same idea as doing what we did here with a single character string, but doing this to a value that's in a data frame column. So str.slice. And then we say our start equals 0 and our stop equals 6. So it's the same kind of index slicing, but it's just done and written out a little bit differently when you do this with pandas. So instead of just typing 0:6, we add this extra stuff here, but it's basically giving us exactly the same kind of process where it's going to go through each one of the rows and do this such that if I run the cell and then I do data.head, we should see we have a new column here. And you can see that we now have year_month, where now we have 1906 and then 01 for the month. And that's true for basically every observation in the month of January. We should see that it has 1906:01 in the year-month column. Okay, let's do one thing here. We'll do a check your understanding and take the break at the same time, and then we'll continue on to our next topic after that. But this check your understanding question in this case is, or task, I suppose, is to create a new column that's just called month, with the information about the month of each observation, but excluding the year. So doing something similar to what we just saw to do the year-month column, your task is to do something that saves only the month for each one of the values in the data frame. And if we do that, you can decide if you want to do that now or if you want to do that when we come back at the end of the break. But let's take 15 minutes. We can continue at 10:38, and you can choose when you want to do this check your understanding.